Okay, hi everyone, and thanks for attending our talk. As being said, we're did some experiments with AI and OpenSearch in particular, which we want to report about today. So just a very quick one. I already talked about that yesterday, so you know that Eliatra is focusing on OpenSearch, and we're doing a lot of development and support and consulting and training, and also offer migration services for switching from Elasticsearch to OpenSearch in particular. If you want, and if you don't have already, we still have a lot of t-shirts at our booth. So at the end of the talk, if you want to grab one, just meet us at our booth and we're gonna give it to you. So why did we decide to do this talk? So I mean, the obvious thing is that everybody's talking about large language models and accompanying technologies. And we think that, and I think everyone thinks that the LLMs are here to stay and they will affect the way that we work in the future. But the question is it now a hype or is it already an overhype? So we just wanted to find out how we can apply practices with LLMs in our daily work. So just a word of warning, so we're presenting two experiments and what we try to do is we try to do a very minimal approach, which means we didn't set up a huge chain of language models and stuff like that, but we just try to use what's already out there, which is in particular ChatGPT and OpenSearch. The results that we got, spoiler alert, were a little bit underwhelming. But there's lots of room for improvement, which we talk about as well. So the first talk will be about using large language models to make technology more accessible. And in particular, we tried to auto-generate Elasticsearch and OpenSearch queries by using natural language. That's what my colleague Leanne will talk about. And I will then follow up with a talk about vector search and the new kid on the block, retrieval augmented generation. Don't worry, I'll explain it later. And for that, I will use OpenSearch, a vanilla OpenSearch out of the box. So, and with that, I'll hand it over to my colleague, Leanne.
Thank you, Jochen. Hi, everyone. Thank you to the OSMC for letting us report on some of our findings. So as Jochen mentioned, in Eliatra, we wanted to see how we could use ChatGPT or large language models in order to improve how we can use OpenSearch and make it more accessible to the general user, not necessarily somebody who's very proficient in OpenSearch or already using these technologies. So just to give you a bit of background on how all this fits together. So OpenSearch is queried via a domain-specific language, and these queries, depending on what type of answers you want to get from your data, can become very complex. So they're large JSON objects. And traditionally, you couldn't use SQL to query OpenSearch. So this meant that if you want to be looking at your data, seeing what it's doing for you, visualizing it, oftentimes somebody with a background in these technologies and not just the average non-tech proficient user could get in and start investigating their data in OpenSearch. So we wanted to use an LLM like ChatGPT in order to try and generate these queries to make the introduction into querying your indices a bit easier. So yes, our investigation was going to be looking into OpenSearch mainly, but given that there's more data in the public domain on Elasticsearch, we decided to do the proof of concept on Elasticsearch because LLMs have a cutoff date, like ChatGPT. There's only a certain date that the information is gathered from and that you can retrieve answers from. So therefore, given that Elasticsearch is around longer, we said we'd just do a proof of concept with Elasticsearch and a large language model to generate these domain-specific queries for us. So with this, I tested the queries that ChatGPT or the LLM generated in Elasticsearch. So I'd use an LLM to generate DSL queries and then pop them into the console in Elasticsearch and see whether or not they were actually valid queries, and we got good hits. So as Jochen said, spoiler alert, it wasn't as great as we would have hoped. We were hoping for higher values, but we've still got things to do to make this a viable thing that we'd like to invest coding time into and more development. But this was just a very simple proof of concept that really anybody could do. There was no programming involved. It was just to see whether this would work using the large language models and Elasticsearch. So Once you get Elasticsearch up and running, you can install these Kibana sample data sets if you're running it with Kibana. So I had the sample data flights, the sample data logs, and the e-commerce sample data set. So you just have your visualizations and your data, and you can mess around with them and query them. So these are the screens, and down here in the that I mainly used, but in the bottom here you can see the console. So once I got those queries from ChatGPT, you pop them into the console, you run them, and you get results back, hits on your data. And if the query wasn't generated correctly, you'd get an error or you wouldn't get the answer you were looking for. So that's what we wanted to see. What percentage of these queries generated were actual valid queries? So yes, the approach was to use the information, as Jochen mentioned previously, that's already there. We weren't trying to make this very complex. We wanted to do it at a minimal proof of concept to see if we just used the data that's already in Elasticsearch that you can get through just hitting APIs that are already there, like the mapping of the indices, and you give this to ChatGPT, then how are your prompts coming back? So we combined it with a human language question. So the idea was you would say to ChatGPT, here's my mapping, and then ask it a human language question like, if it was indices on flights, how many flights have traveled from Dublin to Nuremberg, for example, in the last week, in a human language question. Whereas normally when you're querying your databases, you need to know the DSL, the prompt itself, and that's how you would normally query them. So what we expected was that we would get a valid OpenSearch query from the LLMs that would be generated for us. So yeah, this is what we got from what we fed into ChatGPT. So it was just the mapping. So the mapping of an indices is just the key value pairs. It's how the data is stored. So if we gave that to ChatGPT, we were hoping that we would get back the queries because we'd given it the structure of the data. So this is the curl command that you run, and you're just hitting the API and getting back that mapping. And in my instance, I used Elasticsearch with SearchGuard on top, which is a security plugin. So you have administration login. So you just pass that in as well, and then you get the mapping. So given that that's how I did it in this instance, I've included that was the curl command to get back the mapping. And as you can see, this is the type of information that you get back when you hit that API. So for example, you can see the timestamp field there, and it's of type date. So by giving this JSON object to ChatGPT, we were hoping it would generate perfect queries, which is why we're surprised to see that actually it got it wrong a lot of the times. It seems like a simple enough task. This is just language, so we were expecting it to actually give us better results, but we'll get to that. So this is the proposal and the type of question that we wanted to give to ChatGPT. With the map of the indices, we can give this to ChatGPT. So we would say something like this in the initial prompt. You're a data scientist that works with Elasticsearch. Your data is located in an index, and the data mapping looks like this. Provide the mapping, and tell Elasticsearch to generate a query to answer the following question. And then you just ask the question, and it provides the mapping. So this is the type of answer that ChatGPT was giving back. You can see it's what we're expecting. It's a prompt. It's the query that we're looking to get back. Sorry, the query. So this investigation was done mainly in 3 phases so far. So we started off with ChatGPT, and then we brought in other LLMs like Bard and OpsGPT. And you can see here that the results that we got, the best results we got was 33% hit rate with ChatGPT, with the mapping provided and also a small segment of sample data. So only 33% of the time were those prompts actually giving us back the answers we would expect. So you'd be quicker probably learning domain-specific language and doing it yourself. With these results, there was certainly improvements to be made. And then when we moved over to testing other LLMs, it didn't actually improve. We're still only on low hit rates. So where does this leave us? What do we want to do with this information? You know, it was certainly worth looking into it. As Jochen said, you know, we know that they're the future. They're certainly here to stay. So there's definitely ways that this can be made better. So what we want to do is continue exploring new avenues and also to improve that 33%. If we got a hit rate of about 70% positive results, then that's something we can really consider, okay, will we start getting programming involved? Will we start making this more automated? But where we wanted to start was to provide the minimal that we could in the hopes that we would get better results, to not make the solution more complicated than it needed to be, and just use what was already there, easily accessible from the APIs in Elasticsearch. So yes, we would just extend the data that we supply perhaps, and also be a bit more descriptive, decide on what information we want to give to ChatGPT. And another option would also be to use a fine-tuned model of ChatGPT. So from the ChatGPT documentation, it says that a fine-tuned model will help you get higher quality results than prompting, and you have the ability to train on more examples that can fit in a prompt. So this sounds very promising for what we would need it to do. But we gave this a go. I did make a fine-tuned model of ChatGPT and supplied it with questions and answers that were correct prompts and answers. But we didn't have a large enough sample size to get back the information we wanted. So if we had a much larger sample size, over, you know, thousands of questions and answers, then this would be probably better results. So thank you very much, and I'll pass back over to Jochen.
Thanks, Leanne. So now the question is, how can we actually make these results a little bit better? And Leanne already talked about fine-tuning. That's one way to do it. It's always tedious. It's a long-running process. You need a lot of sample data, so we looked at some other ways to do it. And one of the hot things at the moment is, of course, vector databases and semantic search. And retrieval augmented generation, which I want to explain a little bit and then see how we can actually use it for the task that Leanne was working on. So let's first have a look at the traditional lexical or keyword search, which you're probably all familiar with. So this is still the predominant model when you search for documents in a huge body of data. It's usually based on an inverted index. That's how OpenSearch and Elasticsearch and the underlying technology Lucene works. And it basically says, well, take the words from my query, go to the inverted index and look for a match in the index and just provide me back the documents. This is efficient. It's a proven technology. It's been around for, I don't know, 20, 30, 40 years. And it's effective in the sense that it usually doesn't take a lot of compute power to get back good results from an inverted index keyword search kind of approach. And apart from just searching for documents, there are other things you can do. You can have fuzzy matching, like words that sound like other words. You can search in multiple fields at one time. You can have Boolean searches. A search can really be quite complex, so you can get back very, very specific results. You have your ranking algorithm, which determines the order of your search results, like the relevancy of the search results. This is usually the BM25 algorithm, which you can also fine-tune to your needs. And finally, you can have something like facets. So for an e-commerce shop, for example, just to show me the white or the black T-shirts. And you can have, snippets like text excerpts. So that's all good. But the one thing that we're basically lacking in a keyword search is context. So a lexical search doesn't know anything about the actual meaning or context of your words. It just matches, phrases and words, maybe using Levenstein distance for fuzzy matching, all of this. But it's really just like matching words. And the thing that is now talked about a lot is the vector search, which is also called a semantic search. So this is an attempt for the search engine to understand the context, meaning, also intent, like is this a positive or a negative thing, and concepts. And the way that it's being done is that at its core, it's transforming sources into vectors. So what are sources? Sources can be any piece of information. It can be a text, which is things that we do with OpenSearch and Elasticsearch, but it can also be images and audio. So by using a so-called transformer model, which I'll talk about in a second, you would transform the source into an n-dimensional vector. And then it's all about computing the distance between a vector of your source documents and a vector of your actual query. So it kind of looks like this. So on the left-hand side, you have a couple of different inputs. And in the middle, you have the so-called transformers. And these are, these are LLMs, which are specifically trained to create vectors, also called embeddings, from your source material. And usually, if you talk about the dimensions, it's usually in the thousands. We have models that just generate 384 dimensions, but the usual ones are 786 dimensions. And then you would put all these vectors in your vector database. So what you've basically done is you transformed an input source into a numerical representation represented by a vector. So let's look at an example. Let's imagine that we have a sample data set, and it's just images with captions, right? And it could be anything. And now we search for a phrase like Wild West. So what do we expect that the search engine should return? Something like horses, maybe cowboys, all that kind of stuff. So the expectation is that if we query these data set with Wild West, that documents, captions, with a similar context, a similar meaning, are closer to each other in the vector space. And that if we now transform our query also into a vector, that we would get those semantic hits. So the search results are returned by context and not just terms. So that's basically just a two-dimensional representation. So up here on the right, you have Wild West. You can imagine that broncos or horses or cowboys would be in that area. But on the bottom left, basketball and soccer, of course, don't have anything to do with Wild West as we understand it. So they're very far apart. And just imagine this not being two-dimensional, but n-100 dimensions of vectors. So just have a look at these two different search results. On the left-hand side, you have a traditional result from a keyword search. And you get back an image of a basketball team. Why do you get it back? Well, it has West in its caption like 3 times, and the frequency of a search term influences the relevancy. So keyword search would deem this as a very fitting result. And here on the right-hand side, this is actually a result from a semantic search. And the interesting thing is, if you look at the caption down here, you won't see any keyword like wild or West in this description. Why? Because, well, we transformed this image into a vector, and we transformed our search, Wild West, into a vector as well. And we asked the vector database to look for documents that are close to our input vector, query vector in the vector space. And this is what you get. So on the right-hand side, this is probably, in this very simplistic example, a more fitting result. So let's have a look at OpenSearch. And how we can, test that in practice. So there are all sorts of ways, you can implement that. There are specific vector databases like Pinecone or Milvus and whatever, and then you can combine them with large language models using LangChain and all those tools that are being out there. But I wanted to test the the vector capabilities of OpenSearch. Why? Because, well, it makes things easier, and it promises to be a very, very capable vector database. So since OpenSearch 2.4, and at the moment we're at 2.11, there's a plugin called Neural Search Plugin, which promises to do semantic search for you. So at its core, again, it transforms text to vectors. At ingest time means when you index your documents, the documents are transformed into vectors. And also at query time, when you actually supply the query. The Neural Search plugin supports multiple models. You would usually use a pre-trained model or transformer from Hugging Face, which is kind of a, I'd say, marketplace for pre-trained large language models. If you really want to you could also train your own model and plug it in as a custom model, but that's a very expensive and tedious task. So when searching for similarity or close vectors. The default algorithm is the KNN. It means K nearest neighbor, which comes in two shapes and forms. One is the exact one and the approximate one. The exact one, as the name implies, well, gives you more exact results, but it's really, really compute intensive. So usually you would use something like ANN, approximate nearest neighbor, which is a little bit less accurate, but very, very effective regarding compute resources. Why did I use OpenSearch? Well, we come from the OpenSearch space. OpenSearch is completely free. It's Apache 2 licensed, so you can build your own semantic search solution. You can put it in production. You can sell a product based on it. So there's no license restrictions. It's completely free. So this is basically what we want to do. So when we ingest documents, the documents are handed to the neural search plugin, which, by the way, comes out of the box with your vanilla OpenSearch installation. So you don't need to install anything in addition. Everything's already there. And we want to set up a so-called ingest pipeline, which means whenever we ingest a document, we want to run some additional actions. And in our case, it's handing over the document to the text embedding processor, which then uses the machine learning framework, ML Commons from OpenSearch, to extract the vectors from this document. And these are basically in the passage embedding field, you can see the actual vectors. And the next thing that we need is we need a specific index in OpenSearch, which is capable of running k-nearest neighbor searches. Again, this is built in. We just need to set it up and then can use it. And then at query time, it's basically the same. So you take your query, give it to the neural search plugin, then the sentence transformer model generates the vectors for your query, and then we do a k-nearest neighbor search on the index. This is just an example of a couple of models that you can use out of the box. These are all generating dense vectors. Since 2.11, I think since 2.11, OpenSearch also supports sparse vectors, which is a little bit of a different approach, but I won't go into the details between these two different modes. So let's see what we need to do to set up the OpenSearch for the vector search. So first of all, we need to choose a language model. We choose one from Hugging Face. We then need to register a so-called model group and register the model to the group and then deploy the model. So in this step, OpenSearch would, if not already done so, download the model from Hugging Face, and then deploying the model basically means loading the model into memory. That's all that's to it. Then we need to set up the ingest pipeline where we have our transformer model kicking in, create the KNN index, and then just index the documents into the index, and then we can actually, then we can actually do the queries. So these are the basic steps that you need to do. And I won't actually demonstrate that one live because some of those run asynchronously. So downloading takes a little bit of time, deploying takes a little bit of time. But these are just very plain API calls to register model group, to register model. And you can see here at the name, this is the one that we're going to use from Hugging Face. Again, this is completely free. And then we can deploy the model. We then need to set up an ingest pipeline. And then create the index. And here you can just see we set index KNN equals true in the settings. And then we add the field passage embedding, which is the field that we store the vectors in of type KNN vector. So it's not text or Boolean, whatever. It's a specific type, KNN vector. And we need to specify our dimension for the vectors. Otherwise, it's just a plain index that you can use to index documents. And by the way, you can also use a normal keyword lexical search on this index. So you can basically index a document and then do both, doing a vector search and a regular lexical search. So I've set it up already, like doing the steps that I demonstrated. So maybe first, I need to look here. Let's first have a look at the actual index. So that's how it looks like. And you can see here we have this my NLP index that I just set up. And if we just take that one and maybe have a look at the settings and the mappings. Let's first have a look at the settings. So that's what I just explained. So we have a regular index, and the only thing is that k and n equals true, so we can actually do k-nearest neighbor searches. And if we have a look at the mapping, you can see we have our passage embedding field, and in addition we have a text field. There's an additional ID field that we don't need at the moment. So if we go to the console, and just try to, where do we have it? Just try to index one specific document, like this one here. So if you're familiar with OpenSearch, then you see that this is just a really plain, regular call to index a document. So there's nothing special to it. And if I execute it, then I get back, okay, the document was indexed successfully. The actual magic is happening in the in the ingest pipeline, which runs under the hood. And now if we go back to our index and have a look at the documents, so let's just do a quick search, then you can see down here. So this is the document that we indexed. So we have the text and the ID. And here are our 768 vectors that had been created by the ingest pipeline using the sentence transformer model. So we actually indexed 5 different documents in this index. And just going to do a very, very quick demo, how that looks like. So let's first of all do, where do I have it? Okay, so first of all, let's do just a text search, like a lexical search, with a query Wild West. So, and this one will actually give us, so if I count it, 1, 2, 3, 4. So these are 4 documents returned by the lexical search. We actually have 5 documents in our index, and you can see, well, all the fields have either, all the text have either West or Wild in the body. Now, if we do a vector search, then well, it looks very similar to a regular search. The only thing is that we're querying the passage embedding field. We're doing a query of type neural. Our query text is Wild West, and we need to give the model ID, which of course should match the model that you use when indexing the documents. Otherwise, completely different vectors are being returned. And if we have a look at here now, we have 1, 2, 3, 4, 5. We have 5 different results. And if you have a look at the last one, so here you don't have anything regarding Wild or West. And the reason why it matches, it has some brown bucking bronco, which our sentence transformer thinks is pretty similar in a vector space to our search Wild West. So let's get back here. So what are the learnings? Well, basically, it's a very interesting approach, to a search. However, one of the questions that always comes up when we're working with vector search, why are exactly these documents returned? So you actually don't know why a model chooses to generate, these specific vectors or those specific vectors. So with a, lexical search, you can say, okay, it matches because it has the keywords in it. It has the keywords have a high frequency, and this document is ranked on top because my ranking algorithm is tuned like this and that. But here, that's not the case. So the results are really highly depending on the model. And at the moment, I think the only thing that you can do is, try out different models and see and find the one that matches your use case best. Again, like I said, ranking and scoring difficult to optimize. And if you want to have, a really domain-specific search, let's say you're in the medical field and you want to query medical records, then you probably want to use a specific sentence transformer for it that had been trained on this specific domain. Because if you think about it, the large language models and sentence transformers that we have are general purpose. They've been trained on a huge body of just text, but it's not really specific to one domain. So, and another problem is that the LLMs are frozen in time. Leanne already mentioned that we actually use Elasticsearch instead of OpenSearch because ChatGPT has a cutoff time of 2021, and OpenSearch is around since 2020. So that's a problem. So it doesn't have access to current information. Hallucination, we all know about that. So LLMs will always give you an answer, And the answer will always, or most time, sound really, really great, but you just don't know if it's really correct. Because, well, you don't have access to the actual source anymore. The large language model had been trained on this huge amount of text, and if it gives you an answer, you don't know. Is this a combination of a text from Wikipedia with 20 blog posts and this and that? You just don't know. Now, we did tests with fine-tuning. Leanne did some fine-tuning with our approach to ChatGPT. First of all, you actually need to have very good and very much training data, but it's not possible on the fly. So you need to fine-tune your model before you actually use it. And another problem with fine-tuning is once you fine-tune your model with additional training data, this data becomes actual part of the model. So you can't revert it. One example is always if you're working in the legal field, for example, and you have ever-changing, let's say, legal documents or laws or whatever, fine-tuning is not the way to go. Because once you put one specific text into it, it becomes ingrained or part of the model. So let's talk very quickly about what's now also being talked about and what could be a solution to this one and what could also improve our approach to query generation. It's called Retrieval Augmented Generation, RAG, and it's a way to give LLMs access to information beyond its actual training data. It was published by Meta in a 2020 paper. And it actually combines LLMs with external data sources, but not by pre-training or training the model, but by basically augmenting the information we give the LLM on a prompt level. And the external data source could be anything, but in our case, of course, it's a vector database that we just tried out with OpenSearch. But again, it could be anything. So for example, you probably know that a large language model is very bad at math. It can't do mathematics because, as the name implies, it's based on text. It's based on language. It can give you an answer, what's the square root of 9, because it has seen the answer in some of the training data. But going beyond that, you probably will get wrong information. So the way that it works is that the way that it works with vector databases is that you take information. So let's just imagine you want to build a chatbot, and this chatbot would answer questions about a product you're working on. So you have all the documentation and everything, but you want to have a chatbot. So what you would do is you would take your documentation, you would put it in little chunks, let's say paragraphs, and then you would put it in a vector database. Means creating a vector for all of these little chunks of information. So that's the first step. So in the next step, if a user inputs something into your chatbot, you would take the query again, transform it into a vector, and retrieve the semantically relevant pieces of information from your vector database. And you would then use those pieces of information, those documents, at prompt level and combine the user query, the actual question, with the relevant information that you pulled out of your vector database. So this is a schematic overview how that works. So on the left-hand side, a user enters a prompt or a question. And for RAG, you always have some kind of a retrieval system, in our case, a vector database, but it could be a query against, I don't know, Wikipedia, a calculator, or stock prices, or whatever. So we're doing a semantic search using the prompt that the user provided, retrieve the relevant documents using the semantic search, vector search that we just talked about. And then the important or interesting part is this one here. So we just combine the prompt and the contextual information and give it to the LLM. And by the way, the LLM here that's then actually generating the final response, this doesn't need to be the same one that you used for the embeddings. So there are specific models that are just, they're very efficient in creating embeddings vectors, and there are other models like ChatGPT that are very good on basic language tasks. So this is what's being researched on and used in practice. It's really different from fine-tuning because you can put in all the current relevant information and augment your prompt with information. And that's what we actually did, if you remember what Leanne was talking about. So we took the user query and the additional context information in our first example, that was the actual mapping of the data which we pulled from OpenSearch live. So we pulled the mapping from OpenSearch, just combined it as a string generated the prompt, and then gave it to ChatGPT. So in a way, we're already using this RAG method a little bit, but of course we can expand on it as well. And since we're on at a monitoring conference, I also took a little bit of time to think about, well, what about logs? So also here the result was, well, I wouldn't say underwhelming. I would just say that there's active research going on. So there are a lot of research papers. Most of them are published in 2023. And the basic idea behind this is, well, the raw logs, let's say, are unstructured data. Or you could see it or treat it as unstructured data. And then you could, in theory, use a large language model to transform it into tabular data, to do your labeling, adding some other data, doing anomaly detection, finding outliers, and so on. If you're interested, these are the 4 ones that I found really interesting. They are pretty scientific, I have to say. And again, so we're back to the start. The result of those research papers are, well, a bit underwhelming. So I can tell you at the moment if large language models and vector databases will play a major role in log analytics in future. I can just say that there are already some companies, offerings that are trying to build commercial products with this approach. One is OpenSearch. They just published a blog article boasting about how they enrich their log analytic capabilities with AI. And you have Structured, which is a pretty new one where you have to sign up for a demo. So this is all pretty new. And again, I think that large language models are here to stay. Vector searches, semantic searches are here to stay. Which different areas are affected or will be affected by these new technologies is yet to be seen. But I think it's a very, very interesting field. So we're definitely continuing to dig into it, doing some more research, and then probably come up with our own framework solution, whatever. So that's it. Thanks very much for your attention. If there are any questions, we can either do it now, or if you don't have any time, we're at the Eliatra booth. So if you have questions, just come and visit and grab a t-shirt as well. Thanks.
Yeah, thank you very much for those interesting insights. Are there any questions now? Yes, go ahead.
Just for clarification, did I get it right? The RAG method prevents data from becoming part of the model?
So the question was if the RAG method prevents data from becoming part of your LLM models.
Yeah, that's right. So you have the choice between fine-tuning, that means putting sample data into your model, which will influence the weights of your model, right? So it's kind of then part of the model. But for RAG, we're just operating on the prompt level. So LLMs are, if you just take a look at the LLMs itself and the prompt, they're stateless, right? So if you want to give information or create the illusion of a chat, you just have to do everything on the prompt level. So that's a big difference, and it makes the RAG method more versatile because you can, just plug in any piece of information that you think is relevant for your query. Yes.
Any other questions? If not, then please give a nice applause again for Leanne and Jochen.
Thanks.
And as they mentioned, you can meet them at their booth outside.